Hello, good morning.
Good morning, ma'am.
Yeah, others, only Rohit is there. Others, what about others?
Good morning,
Good
ma'am.
morning, ma'am.
Good morning.
Yes. So in the previous class, yes, my voice is audible, right? It is clear.
Yes,
Yes,
ma'am.
ma'am.
Yeah, and the slide is visible for you all, right? Counters.
No,
No,
ma'am.
ma'am.
No, ma'am.
Now,
No slide is yes, ma'am.
Yes, ma'am.
Now visible,
yeah,
ma'am.
Yes, ma'am. Yes, ma'am. Counters.
yeah. So in the previous class, we have stepped into the sequential circuits. So under the sequential circuits, you all understood the block diagram that it requires a memory element, right? So we have discussed about the different types of memory elements, and then we moved on to the basic memory element, that is the flip-flop. And also we have seen about the conversion of one flip-flop to another. So that is all about your flip-flops. So after that, we have seen the base of your logic circuit. After seeing the logic circuit, we moved into the design of various combinational circuits in your first unit. Similarly, we have seen about flip-flop. After that, what we have seen is we have seen about the different types of flip-flops, their working and conversion from one flip-flop to another. Having understood your base of your flip-flops, now we are going into the design of sequential circuits. So one such sequential or the most commonly used sequential circuit is your counters. Fine. So what is a counter? Any idea what is a counter?
It will count number of ones or
Count the number.
zeros. Name, ma'am.
Yeah,
Like,
very good. Like by the name, the physical significance of the name, counter. It is nothing but it is just going to count your values. Okay, just one, two, three. It can be counting in ascending order or descending order or in any fixed order what you are giving. So a counter, it is also a digital circuit which is used to count the number of pulses. So that day I have told you all, for any sequential circuit to operate, you need clock, and clock will generate your digital pulses, right? So how many pulses is being generated? If you are going to generate one pulse, the counter will count it as one. Then for the second pulse, if it is being transmitted, then the counter will count it as two. A normal thing what we do in our day to day life, like we'll be setting the clock and we'll be looking like when it is 11:15, then the seconds will be rotating for 60 seconds. After that, it will be counted to the next value. Similarly, the counters are those which have the group of storage elements. First of all, you will understood what a counter is, right? It is just a digital circuit that is going to count the number of clock pulses. Simple as that. So you understood what it is. How to build such counters using a digital circuit. So it is very simple. You're just going to employ a sequential circuits of flip-flops. That is a sequence of flip-flops to hold the count. We will see how it is being designed. No other instruments or no other components is required. Only a flip-flop is required. Fine. So in a digital system or computers, actually this is just where it is being used. Okay. This counter can count and store the number of times any particular event or process have occurred depending on a clock signal. So if you are giving a clock signal, then a counter can count how many times the events have occurred, how many times the failure has occurred, how many times you have cleared the exam. All that can be done with the help of counters. So, but the necessity component is you are in requirement of the clock signal. So the clock signal can either increase or either decrease. It is up to the designer. Okay. Now counting means incrementing, or see sometimes no we fix in our mind thinking that counting is always from 0 to 100. That is, we always think it in only in ascending order, but it is not the case. Even in a descending order, the counting could be done. Okay, that only I have told you with respect to the previous state value. We cannot perform this action with any other logic devices rather than counters. What they are trying to say is this is a need. Like if you need a device, okay, need a device which is just fit for counting. That is how many times the event has occurred, how many students have entered the classroom at this particular time. So all this can be done by a simple device, sequential device, that is a counter. Fine. So understanding the need, why, what, all that, we are moving into the types. So as I told you, the sequential circuits are broadly classified into two types. They were nothing but synchronous and asynchronous, right? So similarly, the counters is also classified into two types. It is synchronous counters and asynchronous counters or ripple counters. Very, very important thing you'll have to make a note. That is, in your problems, they will just ask you to design a ripple counter. At that time, don't be thinking it is something different. It is nothing but your asynchronous type of counters. So synchronous and asynchronous. So this type, now I have given this broad classification. So this type is being based on your clock pulse alone. There are more number of types of counters. Okay. Yes, any doubts? As of now, you are clear, right? Yes
Yes,
or
ma'am.
no?
Yes, ma'am.
Yeah. So now we are seeing the two counters. Okay, that is nothing but this counter classification is based on the type of the clock pulse applied. So when the counter is called as a synchronous counter means when the clock signal is applied separately to each flip flop. This only I have also taught you in your sequential circuit classification. A flip flop in the synchronous counters are triggered by the same clock signal. You could recollect that diagram. I have drawn just four flip flops, and for all the four flip flops, I have connected the clock pulse together. You all, I have asked you all the question also, which is faster, which you think it will be faster, whether it will be synchronous or asynchronous. You all told me, ma'am, it will be synchronous because for asynchronous, how the clock will be connected, the output of the first flip flop will act as the clock to the second flip flop. Fine. So the same thing, if you all have understood the broad classification of synchronous and asynchronous sequential circuit, the same thing is there for your counters also. So the counters which uses clock signal to change their transitions are called synchronous counters. So for every instant of transition change, for every small little change, a clock pulse is required in case of synchronous counters. When it comes to asynchronous counters, the counters in which the change transition does not depend, it does not depend upon the clock. What it depends upon, it depends upon the first flip flop is connected to the external clock signal. So just recollect that diagram what I have taught you all, and the reset are clocked by the state outputs at the previous flip flop. So the previous output of the flip flop is connected as the clock to the second flip flop, but for the first flip flop the clock is connected to the external clock. So that only I have taken the diagram once again, like if you all have forgotten that. So synchronous counter, just see here, you're having three flip flops, okay, three flip flops. In that you could see this is the clock pulse, this square wave clock pulse. So now what we are doing is we are giving it separately, individually to each of the flip flops. We are giving it in a synchronous manner. So when it comes to asynchronous or ripple counter, how the clock is connected, this external clock is connected only to the first flip flop. After that you could see that whether it can be q or q bar. Okay, that I will tell you all the difference, when it should be connected to q, when it should be connected to q bar. That difference I will tell you in the later slides. As of now you understand that whether it is q or q bar, it should be, if the clock is connected from this q or q bar, it is called as what, it is called as your asynchronous or ripple counter. Fine. Is it okay for you all? Like you all
Yes,
have
ma'am.
understood? Yeah. So now I have taken the broad classifications. Like as I always tell you all that anything it will have both is pros and cons, right? So now what we are going to do is synchronous counters and asynchronous counters. We are just going to make a comparative study. So as I told you in the previous case, I cannot say that synchronous is the best counter, or I cannot suggest you that asynchronous is the best counter. It is nothing like that. Both are having their advantage as well as their disadvantage, but it is that application, which application you are designing your counter for. Based on that, you should decide the type of counter. Fine. So the propagation delay is very low. Okay, the delay is very low in terms of synchronous counters, and the propagation delay is higher. Then the frequency is high, the operation frequency is very low. Very, very important point. Synchronous counters are very fast when compared to this asynchronous. This point you all told me that day. And the large number of logic gates are required to design. Less number of logic gates are required. Why? Because why this is means, now for every flip flop, the clock signal should be given individually. So the number of wires and number of logic gates that is employed in your synchronous, it is higher when compared to the asynchronous counters. So since you are using larger number of gates, it will be of high cost. This is of low cost, and this is easy to design. Complex to design. Why it is complex is, this flip flop should be designed in a proper manner. Then only you can go for this flip flop design. After this is completely designed, only you can move to this flip flop. So it is like link chain. This is linked to this. This is linked to this. So it is like a link. If there is a error in this particular flip flop, okay, if this there is the error in this particular flip flop, you will be constantly checking this one and this one. But if you forget to check this flip flop, the entire circuit will be wrong. But that is not the case in your synchronous counter, because if,
Nobody told me.
yeah, if this is also not there, if this counter is, sorry, if this flip flop is also not working properly, at least you will get the output of this flip flop properly. Why? Because synchronous input and synchronous output. So at least this flip flop will work properly. These two will not work properly. But when it comes to asynchronous, one is interlinked. We'll all generally call it as they are interlinked to each other. So it is very difficult to find where the error has occurred. So only it is becoming very complex to design. And then the standard logic packages available for synchronous, standard logic packages are not available for asynchronous. What this actually means is, synchronous counter is available in an IC. As a IC, you could find the synchronous counter, but when it comes to asynchronous, a complete package is not being available. Okay. So now coming to the next terminology, what you should know before going into the counter, you will come across the word mod counters or modulo counters. Actually, what that means, without understanding, people start generally have a tendency to design a counter, mod counters. But before that, I just want to make you all understand what this mod n means. Actually, what this mod means, mod is nothing but the different modes of your counters. Fine. It is just going to represent the different modes. Okay, what are the different modes? Now, it also represents the maximum counting capability of the counter. For example, we will take a scenario where you're going to design a 2-bit counter. Okay, so for that 2-bit counter, what is the maximum possibility of counting? I'm telling it is a 2-bit. So what will be the maximum possibility of that?
Two.
Yeah, very good.
Two,
It is,
ma'am.
yeah, it is 2, because the maximum value that counter could count according to your design is, it is 2. It can either be 0, it can either be 1, it can either be 2. So the maximum count is 2. That you all are knowing. That maximum value you are getting, no, the counting capability is nothing but your modulus, or else it is called as mod n. Okay. So now I have taken this formula is very, very important in your modulo counter design. So I'm just taking an example, general scenario. A mod n counter can count up to n events. Just take the example for this n as 2 value. So 2-bit counter can count up to 2 events. Okay, events. We can mathematically represent a mod n counter as small n is equal to 2 power of capital M. Okay, very important formula. So now what is this small n? It is nothing but it represents the number of states. Okay, and capital N, very very important, it represents the number of flip flops connected in cascade. Why I'm telling this step is very important is any counter design, let it be synchronous, let it be asynchronous, let it be modulo n, any counter, irrespective of the type, the main first step, the first step, you will be writing this one only. You will be writing n is equal to 2 power of n. Small n is nothing but the number of states. Capital N is the number of flip flops required. And then you will go for finding how many counts it should reach, how many decimal counts it should reach. So to find out the maximum number of counts, you will use the formula as 2 power of capital N minus 1. So for example, if you are using 3 flip flops, then it will be 2 power of 3 minus 1. So it will be 7, right? 2 power of 3 is nothing but 8. 8 minus 1, it is going to give you 7. So you will be having the decimal equivalent to be starting from 000 to, and it will end at 0111. Okay, it will end at 7. Fine. Yes, any doubts for anyone?
No, ma'am.
I'm getting somebody has unmuted. Okay. So no doubts, right? Shall we proceed? Like you all have understood what these three things, you all keep it in your mind. Three things, that is nothing but 2 power of n. Okay, that capital N denotes the number of flip flops, small n denotes the number of states, and then 2 power of capital N minus 1, that gives you the number of decimal equivalents. These three things I want you all to remember. Fine. Yes, please reply so that I can proceed, or I should wait. I don't know, like you all are understanding or not.
Yes, ma'am. Please proceed.
Yes, ma'am. Proceed.
Yeah.
టూ పవర్ ఎన్ ఉందినా మేడం?
What? 2 power?
టోటల్ టూ పవర్ క్యాపిటల్ ఎన్ ఉందినా మేడం? -1.
No, no. 2 power of this minus 1 is not separate. 2 in power only, this minus 1 also will come. 2 power of n minus 1. This is not for the number of states. This is for the binary equivalent you will write. See, ma, now what he is asking is 2 power of n is going to say you the number of states. Okay. But how many decimal numbers you should write? The binary equivalent. That you can find it with 2 power of n minus 1. Yes, clear?
ఓకే మేడం.
Okay. So, like for the people who are not clear with the previous example, that was a general example. I have taken a example with a number itself. Except taking for n, you all will get confused. No? So, I have taken a number. I have just taken an example of mod 8 counter. See, in your exam, you will get questions like this only. Design your mod 8 counter. So, what will be your first step? Now, what actually this mod 8 means? It means that your small n, see, always students will make a mistake in that they will confuse the n with capital N. So always think that mod 8 means it is nothing but small n is equal to 8. Okay, from the previous equation. Now n is equal to, now we have to find how many flip flops is required. So now we are substituting in this, and you can find that capital N value is nothing but 3, right? Capital N value is nothing but 3. So by with this, you can understand how many flip flops is required. 3 flip flops. But how many states are required? You have to count from, which means it is 3 bits. That also you can understand, like how many flip flops and how many bits. And then it has 8 stable states. Because stable states is given by 2 power of n, so it has 8 stable states. And what are the decimal equivalents? You're going to start from 000 to 7. Decimal equivalent is 7, right? See, this is decimal equivalent. Number of states is 2 power of n. Number of flip flops required is nothing but capital N. Clear?
Ma'am,
Yeah.
for example, if I take mod 23 counter, ma'am.
Yeah. See, very good question. Now, for that, you will not be able to find 2 power of n, right?
Yeah, yes, ma'am. That's what,
Yeah.
ma'am.
Yeah. You will not be, like, always in a mod n counters, they will always give it as a divisible of 2 only. 2 power of, like that only they will give. They will not be asking you to find this one. Fine.
Okay, ma'am. Thank you, ma'am.
Yeah. Others, any doubt? Yes, I think no doubt. Yeah. Now I have generally mentioned you the term as ripple, right? Like I'm telling you, asynchronous is also called as a ripple counter. So I just want to give you the explanation of that word ripple because you should understand each word when you are writing. So what is a ripple? Generally, it is nothing but the output state of the successive flip flop changes their state depending upon the pulses applied to the first flip flop. Actually, you just recollect that diagram. Okay, what is the diagram for asynchronous? Have that diagram in your mind and read this statement. What it actually means is, now suppose you're in the second flip flop, the output of that second flip flop is completely, it is dependent only on which pulse. It is dependent on the first pulse that is applied to the first flip flop. That is, they are speaking in terms of your external clock. Okay, external clock only they are meaning. So whatever you'll ripple, whatever you'll carry forward and go, but your clock pulse is dependent on your first flip flop alone. So that external input, external clock pulse not working properly, if that is not at all functioning, then what happens? The entire asynchronous circuit will be not working. Okay, because everything is interlinked. That only I'm telling again and again. So it is being interlinked. So the output ripples from the first to the last. You all know the general significance of a ripple. Like in waves, you all could see the ripple. So it will be carried from the first end to the last end. So the same thing in asynchronous also, it is being wavering. Okay, it is being carried forwarded from your first flip flop to your last flip flop. Fine. Now you all should correlate, like whenever any questions is being asked, what is a ripple, why you are calling an asynchronous counter as a ripple, then you all can just correlate your ripple with a wave. Okay, C wave. There you could see that it will be propagating from one end and it will end at another end. Okay, there will be no deviation in the middle. Same thing like that only your asynchronous counter also will work. From your first end you are giving your clock, that clock is going to be traveling, it is going to be traveling till the end. Fine. So now again I'm coming to types of counters, because you could remember, like in the previous slide I told that the types of counters are nothing but it is broadly classified based on the application of the clock pulse, the way the clock pulse is applied, whether it is applied to all the flip flops individually or whether it is applied only to the first flip flop. Based on that we classified, but apart from that, based on the usage, how we are using a particular counter, it is being categorized as up counters. Like usage means how you want the counter to operate, whether you want the counter to operate from 0 to 100 or whether you want to operate it from 100 to 0. It is up to your design, up to the designer's choice. So only it is left to the usage. So up counters, down counters, up down counters, decade counters. Can anyone say me what is decade? General meaning. General meaning. Decade.
10.
Very good. Yeah, 10.
10.
So it will be counting from 10 values. Fine. And then there is another classification of counters, that is, it is based on your shift registers. Okay, I will teach you all what is a shift register. Okay. So after seeing what is a shift register, it is one type of your sequential circuit. Like now we are seeing one type of sequential circuit as counters. So after this, we are going to see the next type as your shift registers. So after seeing the shift registers, we are going to see shift register counters. So they are being categorized as ring counters and Johnson counters. So if I complete this slide, no, this entire slide, I'll be completing the topic of counters. That is, I have to cover up counters, down counters, up down counters. So all these category will be coming under binary counters. Fine. After this, there'll be a small topic on BCD counter, because you all know which is a valid BCD number. So we'll be designing a BCD counter. So after completing that BCD counter, we will be seeing about what is a shift register. So after that, we'll see about counter. So this is the flow, like how I have told you for the previous case in your first unit, I have told the flow. Similarly, for this, this is the flow of your second unit. So while you are reading also, please follow the flow so that you all will understand step by step, right? So moving into the asynchronous or ripple counters. So like what to say is when we are coming to the design part, asynchronous counters, we are going to see all these categories. Okay, up counter, down counter, up down counter, and decade counter. Under asynchronous type itself, I will discuss all this. Similarly, again under synchronous, I will discuss all this type. Fine. Okay. So now we are going into design of asynchronous binary counter. So what are the other ways of asking the same question? So only I have given all the types of being asked, the same question being asked in different types. And one more important thing, like I have taught you all this slide, no? This is a gate question. I forgot to tell you all. Like this, they will ask you what to say. They will give you the number of states alone. Okay, they will give you the number of states alone, and they will ask you to calculate how many flip flops is required or how many number of modulus value which is having what mod counter it is. Like that, this is very important gate question. Like under sequential circuit, this will be asked. I will take 2 or 3 questions from gate and show you all in the next class. Yeah. Okay. Now coming to this. So now this 2-bit, 1 second. Yeah. 2-bit asynchronous binary up counter. This is the direct way of asking the question. Otherwise, they could ask it as a ripple counter. Otherwise, they may ask it as mod 4 counter. Okay. Why I'm telling it as mod 4? It is 2-bit. So my n value is going, small n value is going to be 2. So how many states will be there? 2 power of
4, ma'am. 2 power of 2.
Yeah. So 2 power of 2. So you'll be getting 4 states. So the decimal equivalent will be from 0 to 3. So now you could see that very minute things you should note down. In a counter design, whenever you draw, it will seem like, okay, ma'am is just putting 2 boxes and just something she's drawing. No, everything carries mark. Every small thing carries mark. Even this circle, what I have put, no, it carries mark. So I will tell you all. First of all, now with this, you could understand how many flip-flops is required. Small n is equal to 2. So you have understood capital N is also 2. So you're having 2 flip-flops. Okay, I am using a JK flip-flop. It is up to you to decide the type of the flip-flop. It could be JK, it could be SR, it could be D flip-flop, it could be T flip-flop, anything. It is up to the designer's choice. So after that, yeah, tell me.
Ma'am, mod 4 counter means small n equal to 4, no, ma'am.
Mod 4 counter means, yeah, small, no, with this you could not write the small n value. With this only you can write the small n value. This is going to talk about your number of states, 2 power of n minus 1.
Okay, ma'am.
Yeah. So, yeah, where did I stop? Yeah, first you all will draw these 2 flip-flops, fine. And in this clock signal, oh, I have put a arrow mark and I put a bubble symbol down. What that indicates? Can anyone say me? Just say me whether you all know or not so that I can explain and move on.
Negative trigger, ma'am.
Very good. Excellent. So it is nothing but negative edge triggering. Like if you all could remember, I have taught you all about the triggering method. So it is nothing negative edge triggering. So only I put a bubble symbol that it will be indicated in this clock pulse. Okay, that we will see when we are coming to the timing diagram. Before that, what I wanted to say is asynchronous. So asynchronous means from, and it is up counter. See, Arma, 2 words I'm following, asynchronous type, and it is an up counter. So up counter means you should give the clock pulse from your Q. If it is a down counter, you will give your clock pulse from Q bar. Very simple. If it is up counter, you will give the clock pulse from Q, and if it is a down counter, you will give the clock pulse from Q bar. So now you understood what is up and what is down. Up down I will teach you all. So up and down you all are clear. Now that is you all understood. Now after that, what they are trying to do is they are connecting this Q to the clock, and this is being connected to the clock. Now this J and K, they are connecting to the high value. Always the input should be at your high value, because J and K, when it will operate, again come to the base of your flip flop. 1 1 only, you will be getting your flip flop operation, because in your SR flip flop 1 1 will cause what error? What error I told you all? What error it is called as? 1 1
Indeterminate.
indeterminate state, and that error I told you name.
Race, ma'am.
Yeah, very good. Race. RACE. I told you all, like I will ask when I'm coming to counter design also, so you all remember. So now, yeah. So to avoid that race conditions, we will make this both the conditions to be turned on as high. That's all. So the diagram is very simple, but these small things we will note. If you all are putting zero here, sorry, if you all are putting a bubble symbol here, we will note, okay, negative edge triggering they are followed, and then what asynchronous means, we will check whether it is being connected from Q, and it is up counter means you'll have to connect it from Q. So those things and all we will check. After this comes your truth table, very simple truth table. Four states are going to be there. So 00011011, and one more, don't forget your LSB and your MSB. Always your LSB and MSB, students have a tendency to rewrite it. They will just put it as Q naught and Q. No, it should not be like that. It should be in the proper way. So after that, you all know how many clock pulses you all are going to give. You all are going to give 4 clock pulses, because it is a 2-bit synchronous, sorry, asynchronous up counter. Now the timing diagram only, you can understand the operation of this counter itself. What actually this timing diagram is showing you, this arrow mark what I have put, no, it indicates my negative edge triggering. In my negative edge, always I have told negative edge means falling edge, right? So there is a falling edge. So at this particular point only, the transition, the change will occur. Okay, transition is nothing but the change will occur. So now you are giving the clock pulse. Okay, 4 clock pulse is enough. Now what we are doing is, for this Q naught, it is actually 0101. So how you are going to draw? Now, at this falling edge only, this change will occur. Similarly, at this falling edge only, this change will occur, and at this falling edge only this change will occur. So you could find that at your negative edge triggering, every time the counter is counting the values 0 1 2 3, like that it is counting. Nothing, counter is not going to store any values. Counter is not going to be operation as arithmetic operation, logic, nothing it is going to do. Just it is going to count how many number of pulses is being provided. So here it is counting it as 0, here it is counting it as 1 pulse, and again it is counting it as 0. So this 0 means it indicates 0 0, so it will be third value, and then it is again counting it as 1 0, so it is your sorry, fourth value. Yes, so like this only, just it is just going to count 00011011 and so on. So how your second pulse will be, it is nothing but 0011. So how this second transition will occur after 2 stages here. After 2 negative edge triggered, it will happen. After 2 edge triggered, it will happen. Fine. So it is 0011. So it is a very simple explanation, or very simple to design asynchronous counters. Now when it comes to a 3-bit binary down counter. So 3-bit means how many states will be there? 2 power of cube. So 8. Okay, 8. So I am giving 8 states. Now here it is very simple. What we are doing, we are giving the clock pulse. Here you could see that it is what triggering. I have not given that circle. What triggering is this?
Positive edge.
Yeah, very good.
Positive.
Positive edge triggering. And one more difference you could find. What is the difference? Where is the clock pulse given?
Down
Q
counter,
bar.
ma'am.
Yes.
Q bar, man.
Could you find that? So this is why I am putting it in Q bar, because it is a down counter. If here also you are asked in the exam as up counter, then you all will not put like that. So the truth table 0 to 7. So for that you are writing the decimal equivalent. So from this I am drawing the, what is this, timing diagram. So how I'm drawing, now you could see that the changes occur at your positive edge, the arrow mark, positive edge, where it will come, here it will be the change, here it will be the change, and then here it will be the change. So you could see everywhere. See this line and this line. Here you will be having the change, and here you will have the positive change, right? So for every at that particular instance only the changes will occur. This is positive edge triggering. You could correlate, right? Here I didn't put the arrow mark, but I think you all could understand where I'm showing my arrow mark now. So that these are the places where the positive edge triggering will happen.
Yes, ma'am.
Yeah.
Ma'am,
Yes,
So
ma'am.
yeah, tell me.
ma'am, for Q1 it is negative edge triggering, ma'am, in this diagram.
No, 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 no. Q1 it is not edge triggering. Now here in this position only the change is occurring. Here this is positive. This is see for Q
Yes,
naught it will be
okay, ma'am. Okay,
positive. Q1 it will be negative. That and all it is not possible in counter design. If you are
okay,
going
ma'am.
for
Clear.
positive, na it will be positive, and then if it is negative, na it is negative. Fine.
Okay, ma'am.
Hmm. Yes. Any other doubts? Because timing diagram we will be checking in when you all are doing it in that software, no Xilinx software. So timing diagram you all should be very familiarized. Like what you are getting, whether you are getting the correct answer, you all should be in a position to verify that. Fine. Yes. I think no doubt. Yeah. Before going into this, like asynchronous, no, like one more topic I have left. It is up down counters and decade counters. Now I will solve it in video mode, up down counters for you all, okay, because there some little bit, it will be a little bit complex compared to this, so that I will solve it. After that we will move into this synchronous. Okay, after we are seeing up down counters, we will move into this synchronous. Yes, I think that sheet is visible for you all, right?
Yes, ma'am.
Yeah. Shall we go for the design of up down counter? Like you all have in your mind asynchronous type itself. Fine. Don't confuse with synchronous, but because since we have not moved into synchronous, I will show you all how to design a asynchronous up down counter. So what is the other name for asynchronous?
Ripple.
Very good. So asynchronous up down counter. Yeah. So now you will be having a doubt. If it is up counter, ma'am is telling to connect it from the Q. And if it is down counter, I am telling it you have to connect it from Q bar. Simple as that. Up down means what to do, when to select it as up, when to select it as down. So at that time itself, a word comes to your mind. You have to control. Yes or no? You have to control that circuit. When it should operate as up and when it should operate as down. Is it visible what I'm writing?
Yes, ma'am.
Yeah. So there you need a control, right? You need the control operation when it should be up, when it should be down. So how that control will be done is we are having an option like we are going to make m is equal to 0. I will tell you what this M and all is. Okay, we will see in the design. So we'll be having this down. If it is going to down, it is going to operate as a down counter. Then we will fix this small m value is equal to 0. And when it is going to operate as a up counter, we will make this m value is equal to 1. This is the first step you should understand. Na? Like when you're going to asynchronous or synchronous anything, when it is coming as up down counter, what you should have in your mind is up down means there requires a signal called as control signal in order to control the circuit, whether it should operate as up counter or whether you should operate it as down counter. So how to control? You need a control signal. So what is that signal? That signal, if that value of that signal is 0, then that entire circuit will operate as a down counter, and when that entire signal is 1, it will operate as a up counter. Very simple. Fine. Now, after understanding this, how to control, how you can incorporate this control sequence into your flip flop. So it is very simple that now I will just directly go into the table. Okay. So let me take it as M, and let me take it as Q, and let me take it as Q bar, and we'll be finding Y. So what I'm going to do is I'm going to have it as, for the first instance, no, I'll be having it as 0, 0, 0. Okay. This indicates that it is going to operate as a countdown. So 0, 0, and then 0, 1, 1, 0, and then 1, 1. Fine. Simple. Okay, this is going to operate as your count down. Now when it comes to count up, 1, 1, 1, 1. So what will happen? 0, 0, 0, 1, 1, 0, 1, 1. Okay, I could show you this one as, this is nothing but your, this will be down. Okay, it will count down, and this will be up. Fine. So this is your countdown, and this is your count up. That this time the circuit will operate as a down counter. This time it will act as an up counter. So what will be your outputs? How it will count? So it will be like normal. Here you will be having it as down counting. So down means it will be having it as 0, 1, 2, 3, and here it is up counting, right? So it will be, sorry, here it will be 3, 2, 1, 0. And here it will be 0, 1, 2, 3. So here it is counting up the up values. That is from up counter means it will be counting from your ascending order. Here it is descending order. Simple as that. Fine. See, this 3 is, now you all may get a doubt like, ma'am, the value of 3 is not 1, 1, right? Actually, it is 1, 1, but here I put it as 0. This 0, 1, 2, 3, 0, 1, 2, 3 has no significance with your binary equivalent. Be very clear, equivalence with your binary equivalent. It is just the indication that that many pulses has been counted. Simple as that. That many pulses has been counted. That's all. So after doing this, I have told you this control signal. So this control signal is made up of certain logic gates, and those gates are called as decoding gates. Again, combinational circuit comes into the play. What is this decoding circuits? What are these decoding? How you can design decoding? Very simple. First, you are going to take your M signal. This is your input signal. So if you invert it, this is nothing but your NOT gate. Okay, you are going to invert this and give it to a AND gate, and for this AND gate it is Q bar. And if you are giving it directly to one AND gate, and if you are multiplying it with Q, okay, these two things, it will be odd, and you will get you the output. So actually what is happening, MQ, and here it is MQ bar. So these two things are getting odd operation. So this is the entire circuit,
Ma'am,
that is this,
M bar dot Q bar, na ma'am.
which one now? Yeah. Very good. M bar dot Q
The
bar. Yes. Yeah. M bar dot Q bar. So actually what you're doing here, what are these decoding gates? Why I have to always take this combination? Why this is the structure? Why? Because it is used to indicate, whether the connected signal is high or low. You could, now he told me the correct things here. Now this indicates low, and this indicates high. Very simple, right? 0, 0, 1, 1. So this combination indicates it is completely low, and this combination indicates, so binary equivalent of, here we are putting it as 0, but in logic gates, how to represent this 0, we have used these gates, and in binary, how to represent, sorry, in logic gates, how to represent this one, we have used. Simple as that. So, okay, now you understood this one. Now, where to place this? Now, where to place this in my flip-flop? How my circuit will look? Whether it will look as complex? Yes, it will look as complex. This particular circuit is going to come in between each of the flip-flops. I will draw and show you all. That time you all will understand the complexity of your up-down counter. But this is a very smart way because a circuit design you're doing, it should be operating as both, right? It should operate as both your up as well as a down counter. So if it is in that way only, it is helpful. So practically, this counter has huge applications. See, I'm just taking 3-bit, okay? 3-bit, so I'm using 3 flip-flop. I'm using a JK flip-flop, fine. So this is going to be my QA and this is going to be my QA bar. This is going to be JB. Yeah, fine. Okay. Now, what triggering we will use? I will go for negative edge triggering, okay? So you can use any triggering. I'm going for negative edge triggering. And now we are under asynchronous type. So the external clock pulse will be only 1. And I'm making my this circuit to be here. How I'm going to make it? Very simple. I'm just drawing the same thing. Nothing more than that. I'm putting 2 and 1 or. Fine. And this is going to act as the clock pulse for my next negative edge triggered clock pulse. Very, very important. Negative edge triggered clock pulse. So here I'm going to put the control signal M. Now M can be a straight line and this is your inverted line. Like this you draw. So now what happens for this gate? This will come, right? And this is nothing but QA bar is here and QA is here. So now from this it is this one. Understood, ma? First this, how I'm correlating it with the flip-flop. Yes or no? Any doubts for anyone? Yeah, you all may ask me another doubt. Like where this JK will be. This on to high. High is nothing but one value. Yes, any doubts? Shall I draw this here also? Any doubts for anyone? Yes or no?
No, ma'am.
Okay. So two and one or. So here it will be as a negative edge triggered clock. Okay. And then here you are going to get this. And here this will be connected. This will be connected. So the same diagram. So I'm connecting here. And from here, this is my Q bar line, right? So this Q bar line, I'm connecting it here. Fine. So the similar thing you will connect it like this and here you will take your output. Okay, so this circuit you are seeing, this entire circuit you are seeing, so this is nothing but I'm using 3 flip-flop. It is asynchronous 3-bit, okay, up down counter. This is the, what to say, this is the significance or how you are going to draw your up down counter. But what are these decoding gates? What happens in these decoding gates? So you know the operation of this AND gate and this OR gate, right? So now for
Ma'am,
instance, yeah,
excuse ma'am, the screen is stuck, ma'am.
screen is, screen is,
The screen is still, ma'am. It's not moving.
oh, now,
Yes, ma'am.
yeah. So now you could see that, for example, now I'm just going to explain the operation of this decoding gate. See, they'll be asking you what is the structure of a decoding gate. So you should draw this structure only. Okay, 2 AND gates with 1 OR gate. Now I'm going to explain you what is the operation, what exactly happens here. So now for instance, you take that if this counter, if the output of the decoding gate, if this value, entire value goes high, for instance, I'm telling. So if this equal to 1, at that time what will be your JB and KB value? So here also you are giving it as high pulse. But if your decoding gate is becoming 0, at that time this J and KC will be turned on to 0. So it will be switching over from this operation to this operation. Fine. So we'll be seeing more examples on this up down counters so that you all will be getting more clear idea. Just I have solved one 3-bit problem. We will solve using D flip flop. Right? Now I have solved using JK flip flop, but you all should understand if up down means there is a requirement of a control signal, and that control signal is nothing but M. You can take any alphabet, and if it is up means M is equal to 1 and down means M is equal to 0, and this is the way, and this is how the control signal is being controlled, and this is the operation. Fine. If this is clear, in my next session, that is Thursday session, we will see about one more example on this asynchronous counter, and then we will move into your hello.
Okay, ma'am.
Class,
Yes, ma'am.
class. 1 second. கூப்பிடுங்க. Hello. Yes, ma'am. Clear, right?
Yes, ma'am.
Yeah. So in the next class, we will see about that. And one more clarification, like all of you all were saying about that MATLAB, right? You all were not able to access or something. So for that, I have found a solution. Just people just solve it and keep it. No need of writing or doing it in MATLAB. Just solve addition, binary addition, division, conversion. Just solve it and keep it. Fine.
Okay, ma'am.
Okay, ma'am.
Yes, ma'am.
Okay. Like when this
Thank
issue is getting rectified, we will try to do it in MATLAB. Fine.
Okay, ma'am.
Okay,
Yeah.
ma'am.
Any doubts for anyone like
No.
this topic? And one more thing, no one reminded me about that link. I didn't post that submission link, and no one reminded me this time. When you
Ma'am, we don't.
yeah, there, tell me. Yes, ma'am, tell me. I'm listening.
Nothing, ma'am. Nothing.
No, just say me like whether you'll over, you'll complete it more time. That three
Ma'am, we
questions
need more time, ma'am.
you'll
More
need
time.
more time. Okay, till which we will keep Saturday.
Okay, ma'am.
Because I should give task for these topics also, no? Like I'm not giving task for these. These are very important topics. I should give task for all these also. So see,
Yeah. Okay.
we will fix it like this. We will fix it like this. Like Saturday, you'll submit those 3 questions, okay? On Saturday, what I will do is this week, what and all I have taught you all under sequential circuits. I'll prepare 10 questions and I will send you all. In that one will be open ended. Fine? Because you'll ask me.
Okay,
Fine.
ma'am.
Yeah.
Ma'am, can you explain the third question, ma'am?
Yeah, I will. You all want me to explain it, or after you all submit? I thought I will explain to you all.
Oh, okay, ma'am.
No, ma'am.
Yeah.
Like what you all will do is you all do what you all understand. Okay, because this is not going to carry much marks. Okay, what you all understand, you all do. Fine.
Yeah, yes, ma'am.
If it
Okay,
is
ma'am.
wrong, also it is okay. But after that, the next session I will explain the answer for all the 3 questions. I just want you all to have a try, and I want each one of you all to do that simulation also in that app. Because that time you all told you all didn't have time for exam. So this time I want you all to do it in app also and submit it. Fine?
Okay, ma'am.
Yeah. If no doubts, you all may leave. If you all have doubts, people may ask me.
And what about MATLAB?
MATLAB, I told you, no, ma. Like you all can stop doing in MATLAB. That we will see later. Those questions you all just do it normally. Like you all solve it in and then submit it. That's all. Don't want MATLAB code. Yes. Any other doubts?